And as our next speaker, we have Peter Bühlmann from Zurich.
Okay, thank you very much. It's a very special honor here to give this lecture, and I'd like to acknowledge my main collaborators for this research, Jonas Peters, Nikolai Meinshausen, and Dominik Rotenhäusler. So, invariance, which we see also in the title, as I'll explain, has lots to do with causality. And I'm citing an old verb here, happy is she who is able to know the causes of things. And already people in the ancient times have debated on causality, and it is a very central issue, obviously, also in science. So we'd like to address a bit these issues here. The word causal is very ambitious, if you think about it. It's also maybe very philosophical, and we'll discuss it today as a prediction problem, actually the effect of an outside intervention, which makes it more pragmatic and perhaps less philosophical. As a warm-up exercise, I want to convince you and illustrate a bit that correlation is very different from causation. And so I'm a statistician. I show you some sort of real data, and here is a real data analysis. So on the x-axis, you see chocolate consumption in kilogram per years per capita, and on the y-axis, you see the number of Nobel laureates per 10 million population. And you see almost a perfect correlation here. The correlation, the empirical correlation, is 79.1%. And if you see these kind of data sets, of course, people out there start to interpret these things. And so here is one study which says eating chocolate produces Nobel Prize winners, says the study. And there's another one which says, well, geniuses are more likely to eat lots of chocolate. And obviously, there are a couple interpretations, and here are maybe the three major ones. You can mathematize this problem a bit. X is a variable, it's a chocolate consumption. Y is another variable, it's the chance to get a Nobel Prize. And now the mathematization of the causality is a directed graph. So that would be chocolate produces Nobel Prize, X would point to Y. The other interpretation would be geniuses eat more chocolate, so Y would point to X. And the third one, which is probably the obvious one, is there is a hidden confounding variable, something which you do not observe in the data set, and that creates the spurious correlation. Okay, well, you might have your own theories if you have these results. And obviously, it would be very helpful to do an experiment. And actually, in statistics, we do randomized, controlled experiments, forcing some people to eat lots and lots and lots of chocolate. So I decided actually to do that experiment with you. So I randomly assign it, and some of you will catch a chocolate. This is fully randomized, and some of you not. And the point is that I really do this in a fully randomized way. So the ones who receive the chocolate, they are forced to eat chocolate every day over the next 20 years. They have to eat lots and lots of chocolate. The other ones who didn't receive a chocolate, they're banned to eat any chocolate for the next 20 years. And then we wait for a long time and we see what happens. And if there is a dependency left, it must be that X would cause Y, that if you eat a lot of chocolate, it must increase the chance to get a Nobel Prize. Of course, you have to promise me you would have to report to me if you win the Nobel Prize. So this is considered to be actually the gold standard. Obviously, experimental perturbation or intervention is very informative. So what we do here, we perturb, and then we want to see what happens. And the other part is the randomization is also very crucial, actually, to break the dependence to potential hidden confounders. If you wouldn't randomize, we couldn't break it. So it's very important to do this in a randomized way. Randomized controlled trials, I mean, they exist, of course. They're very powerful. But they can be highly unethical. So if you didn't catch a chocolate, this is highly unethical. There's a long time horizon involved. There are issues with non-compliance, that reliability of participants. There are high costs, and so on and so forth. And so what I want to discuss a bit today is what can we say if we don't have a randomized controlled trial? What can we say if we don't have the gold standard? And my point is, okay, we should look at this as a prediction problem. And actually, if you think about causality, it is something like, and I'll give a more mathematical definition later, it's something like a quantitative answer to a what if I do question, an answer to a what if I perturb question, but without having data on that experiment. So actually what we want to do is we want to predict the outcome of an unobserved manipulation. We want to predict the outcome of an unobserved experiment. So mainly modern applications are faced with this problem. So here is one in genomics. This is one where I'm personally more involved in. A question could read as follows: what would be the effect of knocking down, of manipulating a gene, say, on the growth rate of the plant? The point is we have no data on this gene perturbation, but we want to predict that. Another question would be, say, in e-commerce, this is very popular, what would be the effect of showing a person XYZ an advertisement on social media, but you have no data on this advertisement campaign for the person XYZ or persons similar to XYZ. I'm using here the subjunctive would because I want to predict that without having seen data on these perturbations, on these interventions. Okay, so here is again a cartoon of what we're trying to do. We have two variables, X and Y. This is synthetic data. I see them. This could be chocolate consumption and Nobel Prize. And you could fit a regression line here. And now you're doing a manipulation. You set the value of X to -8. And the question is, what is the predicted value for Y? And most of you who have listened to regression courses, they would make the prediction here, okay? And that, of course, corresponds to the causal pattern, X causes Y. In that if I manipulate X, it has an effect on Y, and the effect is according to the regression strength. But the other scenario is also quite likely. I could also predict here, and that would correspond to the other version. So Y would cause X. If I manipulate X, nothing happens to Y, and I would make my prediction just the mean of the Y values. And so this is synthetic, but actually this is real. This is a real problem. So here are activities of genes. These are gene expressions of yeast. And here you see the activity of an X gene, here the activity of a Y gene. You observe something, that's the blue data cloud. You can see a regression strength, and you do a manipulation on the X gene. And then what happened if you do this perturbation, actually the Y gene changes more or less according to the linear regression line here. And this is another example. So I have an X gene, a Y gene. I observe the data, the blue point cloud here. I see a regression dependence. I manipulate the X gene, and nothing happens to the Y gene. And so the question what I wanted to address is how can we predict whether it should be here or there? And this is actually a challenging problem. So how do we predict this? It's an unusual statistical problem. And the idea, maybe that's a bit more conformal or kind of usual to statistics, we somehow want to borrow strengths from other perturbations. But I should make the point clear here. If we know, say, the probability distribution of a system in steady state, we cannot address this question. So that means, or that translates, if you just run regression, if you would run a nonlinear deep neural net, it could not address this question. The problem is the directionality, whether X points to Y or Y points to X. This is not a linear or a nonlinear regression problem. And we need some perturbation, some heterogeneity in the data. This is something very natural to scientists, but maybe not so usual to the classical statistics, but we want to exploit that. Of course, many people have worked in causal inference before. So Neyman, in his master thesis, propagated a potential outcome model. He gave a first mathematical formulation. There were many other people. People worked on graphical and structural equation models, and so on and so forth. So this is all nice, this is all good, but we propose here something different. namely to exploit unspecific heterogeneity. Maybe we have unspecific perturbations, we don't quite know what it is, and we want to exploit that. So this is heterogeneous large-scale data. This is a cartoon picture. And I try to convince you that we can take advantage of heterogeneity, which often arises in large-scale data where an IID or a stationarity assumption are not appropriate. And so here's my setting. I try to give here the framework. So we assume that we have data from different known, I call it environments, or I could call it an experimental condition, or a perturbation, or a subpopulation, and I denote them all with a little E for an environment. So my data comes from known environments, and the space of these environments which I observe is my script E. So script E is the space of observed environments. I'm thinking of a regression, classification type problem. I have covariates, I have a response, a variable of interest. They have a distribution F, and the distribution always depends on this E, on this subpopulation, or on this environment. Simple examples, you can think of, you have data from 10 different countries, you encode these countries with your subpopulation or environments. E is 1, 2, up to 10. Or you can think of different economical scenarios. Now the different environments are different time regimes in the data. Typically these are blocks of consecutive observations, and I have various different environments. Okay, so script D, this is an important quantity. This is the space of observed environments which I've seen in the data, like my 10 countries. Now I consider many more environments, many more perturbations, and they're denoted with a script F. So script F is a much larger space than script D. These are many more perturbations, many more environments which I have not seen in the data. In my examples from before, script F could be the 10 countries which I have in the data, and maybe all other countries in the world. From them I have no data. Or in the economical prediction problem, it could be the scenarios which I have until today, and very many potential future scenarios which I have not seen in the data. And so here is my prediction problem. Predict y given x, the usual thing, such that the prediction works well or is robust for many possible environments in this script F, which I have not seen based on the few environments or heterogeneities which I've seen in the data. Okay? This is my prediction problem, so this is a very pragmatic problem. Predict y given x such that prediction works well, is robust for all these many possible environments in this large space script F based on data from much fewer environments which I observe in script D. Now we can use a bit of mathematical formulation for that. For example, in a linear model, we can try to solve this problem. I look at a worst case risk over many environments in this script F, in this large space, and I try to find a regression parameter which optimizes this worst case risk. Okay, people would call this robustness. This is kind of a robustness quantity to a certain extent. Now, I try to tell you a bit, causality has something to do to predict an answer to a what if I perturb, what if I intervene question. And causality in that sense is really prediction for new unseen scenarios, new unseen environments. So I try to argue, and we'll make that more precise, this is not only robustness, this has also something to do with causality. I try to optimize a worst case risk over a class of perturbations, and causality has something to say here. Actually what happens, this is a bit in a nutshell, I take this result a bit early. If I look in a linear model, and if my perturbations are all perturbations, they're very strong, but they're not allowed to act directly on y, I'll define that later what it means, then the solution of this worst case risk optimization problem is what people call the causal parameter, and I'll define that as well. The point here is really causal parameter optimizes a worst case risk, and that's a bit a new viewpoint. Usually people talk very differently about causality, but here we see a connection that actually the causal solution optimizes a worst case risk. And we'll discuss later models for this perturbation class script f, models for the perturbation class script d, and make these relations more precise. Okay, so how can we exploit heterogeneity in the data? So I assume I have this heterogeneous data, I have my observed heterogeneity in this script d. And we have here a proposal, we call it invariant causal prediction. And I'm taking a main message already away on this slide, which says, and then I'll explain it later, causal structure, causal components remain the same for different perturbations, different environments, while the non-causal components, they can change across environments. And so this leads to a very simple principle. I only have to look for stability of structures among different environments, among different perturbations. Now the question is, of course, how do you define stability? What kind of stability measure you look at? And so here it is. So this is an invariance assumption, and I'll discuss that a bit, but that's our stability measure, how we measure stability over different perturbations. So this invariance is a key assumption, and here is the assumption. It's invariance assumption with respect to this script D, the space of observed perturbations. The assumption reads as follows. There exists a set S star. This is a subset of the covariates. So my covariates are indexed by 1 to d, so this is a subset of my covariates, such that if I look at the conditional distribution of y given x S star, I condition on S star, this conditional distribution is invariant across the perturbations. Okay? So if you translate that to a linear model setting, it would be the following. You would translate this as there exists a regression parameter vector, call it gamma star. It has a support set, it's S star, such that for all perturbations in my script D, I can write YE, the response, is XE, same gamma star, plus an error term. The error is as usual uncorrelated from S star, and the error distribution is the same for all perturbations for all environments. Now the environments create typically different distributions of the x's, but the conditional distribution is required to remain invariant. So we will discuss, of course, whether there exists set S stars and so on and so forth, but that's my assumption. So from a practical point of view, you can say, okay, gamma star S star is interesting. So if you're an applied statistician, if you condition on S star, then all of a sudden you see the same regression coefficient and the same residual terms, and that's interesting. Okay, now we require the invariance assumption not only with respect to this observed set of environments, but we're looking at this script F, this much larger space of potential future perturbations. Okay, the invariance assumption reads the same, and now there exists a set S star such that the conditional distribution remains invariant across all perturbations in this much larger space script F. That's a stronger assumption. And say in a linear model setting, the set S star and the corresponding regression parameter gamma star are even more interesting because they say something about new unseen environments. Okay. Now I link this to causality. I link this invariance assumption to causality. I need to define one version of causality. There are many, and here's a very mathematical definition. I have my random variables, they're nodes in a graph. I have a causal influence diagram. The causes are encoded by directed arrows. It doesn't need to be an acyclic graph. It could have feedback loops. So this is my discrete structure. And now I put a quantitative model on the graph, and this is called a structural equation model. So here these little arrows, algebraically, they're equal signs. And so it would read as follows. My y variable is a function, could be a nonlinear function of the parental variables only, here of x11 and x8, comma error term. And all the x variables have the same sort of idea behind, so xj is a function of the parental variables, comma error term. And it's important that these error terms are mutually independent, so that actually excludes hidden variables for the moment, but I'll come back to that. So what are the causal variables for y? This is very plausible and intuitive. People would say, and actually define it this way, the causal variables for y are the parental variables. This is x11, x8. And typically the task is, given data, I want to infer x11 and x8. Okay? So how can we link invariance to causality? And so this is a bit explained in this slide. So the problem I want to look at is under what model for the perturbations can we have an interesting description of the invariant sets which satisfy the invariance assumption. And here are the main two assumptions, and the third is not really an assumption. The first one is I require from my perturbations that they do not act directly on y. What do I mean by that? Well, in the structural equation model world, you can write it down. These are kind of the environments. This is now a variable, and it has an effect on x. Here we have kind of effects between x and y. X is multivariate, but there is no arrow from e to y. That's the one main assumption. And the other main assumption is the environments, the perturbations, do not change the mechanism here. That's a major assumption, but we make that assumption. Now, typically the environments, they change the x's a lot. So perturbations change the distribution of the x's, and typically we write it this way, we delete the arrow from e to y. And then it's very simple to prove, but it's an important message. The following proposition: you have a structural equation model for yx, you have a model for the perturbations. Now we have a model for the perturbation, and we ask that the perturbation in this script f, the perturbations which I have not seen in the data, are such that they do not directly influence y. They do not change the relation between x and y, but typically they change the distribution of the x's a lot. And then it's very simple to prove the causal variables, the parental variables of y, satisfy the invariance assumption. Okay? So causal variables lead to invariance. That's important. That's interesting. Under arbitrarily strong perturbations which do not act directly on y. And so, thanks to this proposition, it becomes very plausible that the solution of this optimization problem is the causal parameter. So if I look at all perturbations which do not act directly on y, they can be very strong. If I have a worst case risk, I should condition on the causal variables, because then I have an invariance, and then it's a simple thing to show that actually the optimizer of this problem is the causal parameter in a linear structural equation model. So if the perturbations would not be arbitrarily strong, the worst case optimizer is different. It will not be the causal solution, and I'll talk about that. So let's also check a bit whether these assumptions make sense. I think this is quite important if you try to deal with some applications. So this was actually a project I was involved in. So y is the growth rate of the Arabidopsis plant. X are very high dimensional gene expressions, so you measure the activities of these genes. And we have actually perturbation in the lab of this plant, and the perturbations are just gene perturbations. You knock out gene 7, you knock out gene 20, you knock out gene 123, and so on and so forth. And now think about these assumptions. Now, it's plausible if you perturb the gene, it will not directly act on y. It will not directly act on the growth rate. That's a very plausible assumption, and so this assumption is fulfilled. The other one, I have no clue. If you perturb your x, it might change the mechanism between x and y. That's a very hard problem, but you have to make some first-order assumptions, otherwise you're completely lost. Obviously, if you perturb the genes, the x components will be shifted a lot, scaled a lot, and so on and so forth. So the first assumption is very plausible that it holds. The second one, it's unclear. I just argued a bit that causality has to do something with invariance. And actually, the causal variables, they lead to invariance. But this is nothing new. This is known since a long time. Havelmo had it implicit in his work. So here's a picture of Trygve Havelmo. He was a Norwegian economist, and he received a Nobel Prize, so he probably ate a lot of chocolate. So he knew that the causal variables, they lead to invariance. And what we want to do is the reverse relation. We want to exploit the reverse part. Can we deduce or conclude, if I see invariance in the data, can I say something about the causal structure or predictive robustness to solve a worst-case optimization problem? So we want to go the other direction. And this has not been exploited before, maybe also because there was not good data around. I want to have heterogeneous data where I can find invariance and then conclude from that. So this is the search for invariance and the causality. So if you want to go this direction, and for the experts here in the room, it's clear this is impossible in general. There are severe issues of identifiability. Many causal graphs or many different graphs would give you the same distribution according to the Markov factorization. So you cannot expect that you can solve this problem completely. Nevertheless, what you can do just from a pragmatic point of view and how the whole thing is set up is, well, I can check in the data, I can run a statistical test whether a subset of covariates satisfies the invariance assumption. So I need to check whether the conditional distribution, if I condition on such a set S, whether this is invariant across my perturbations, my environments, which I've seen in the data. These are the observed environments. In general, that's hard. In a linear model setting, that's easy to do. If you assume Gaussian errors, there exists an exact test. So this is an F-type test. So that's back in the 60s. They proposed how to do that, of course, in a completely different context. So what you can do statistically, you can collect all the sets of covariables, call them S1 to Sk, which are statistically compatible with the invariance assumption. Okay? Now there's this identifiability issue, and we address it as follows. So here is my estimator, my algorithm S hat. It depends on this observed set of heterogeneities. I simply intersect all sets S which are statistically compatible with the invariance assumption. Okay, statistically you can do that. You can do that with a certain significance level, say alpha 0.05. And then if you do this, the theorem is as follows. You assume a structural equation model. We assume a linear model for y versus x and Gaussian errors, so we have an exact test, but otherwise you can do it also for nonlinear problems. And then it's the same thing what I explained before. The perturbations in this observed set of environments, they do not act directly on y, they do not change the relation between x and y. These are my main conditions. Then this algorithm has a property that it controls against false positive causal selection. So S hat D must be contained within the set of causal variables with controllable probability 1 minus alpha. So that's good. So if you run this on a data set, if something is in S hat D, you know it is a causal variable. Maybe not all of them, but that one must be a causal variable. It could happen that S hat D is the empty set. Well, bad luck. I'm not saying anything about power of this method, but if you use this method, you have a control against false positive selection. You will not claim a false causal relation. We call this ICP invariant causal prediction, and I want to show you a bit how this actually works on a real problem. And the problem is really challenging, and we have been working on these kind of problems since a while, and this is so far maybe the best what we can do. So this is single gene deletion experiments in yeast. So we have yeast, this is baker's yeast, this is used for baking the bread in the morning. It has about 6,000 genes, and we measure the expression of these genes. And I have a response of interest, y, I put it in my framework, y is the expression, the activity of the first gene, and what are the covariates? The covariates are the expression of all other genes. Now I can do it again. The response of interest y is the expression of the second gene, the covariates are the expression of all other genes, and so on and so forth. I can do this 6,170 times. And the goal is predict the effects of unseen new single gene manipulations. What would happen if you knock out gene 7? Give me a prediction of that. Okay? Here's the data. We have collaborators in the Netherlands. So we have 160 observational samples. This is a lot. So they measured 160 times this yeast in steady state. It was quite expensive, but they did it. And they manipulated 1,479 single genes. So they knocked out single genes 1,479 times. Okay. So now, how does that fit in this sort of framework? What are the environments? So here we have replicates, that's good. Here we have no statistical replicates, so we pool them all together. This is very crude, but the theorem allows me to do that. So we use just two environments. One are the observational samples here, and the other one are all interventional samples. You put it into an environment. Now we do kind of a statistical validation. we train this method, this algorithm, on all observational data and 2/3 of the interventional. I put 1/3 of the interventional data aside, 1/3 of the perturbation is put aside, and I try to predict that. Of course, I can repeat that, and I do a multiplicity adjustment. These are some sort of the usual statistical tricks. So what happens here? On this problem, 8 genes are causal variables. So the algorithm says 8 genes are causal for another one. That's great. I have my control against false positives. So, well, question is whether the assumptions hold, of course. So you think this is great. It can also be disappointing, because if you think about this, say, in a graph, you have 6,170 genes. I have a graph with 6,170 nodes, and I only see 8 directed arrows from one to another one. So I don't see much. I only see little, but hopefully what I see is real. And the point is, of course, I can validate, because I have put 1/3 aside, right? So now I validate. So how do I validate? So we look at these strong intervention effects. So here is one. So you have observed data, you make a manipulation, it has a huge effect. The kind of corresponding y value is out of the what you observe in the data. This is a strong intervention effect, and that's not a strong intervention effect. So you make a manipulation on the x gene and nothing happens with the y gene. So 6 out of the 8 are strong intervention effects. 2 we don't know, but 6 out of the 8 are strong. And in statistics, we typically look better at something like this. This is an ROC type plot. So on the x-axis, you look at the number of predictions you do. I have maybe my first prediction, my second prediction, my third. And on the y-axis, I look whether the prediction was a strong intervention effect or not. So this invariant causal prediction is the red line. And what happens here is quite interesting, I think. So the first top prediction, so the method said, okay, this is the top prediction to be causal for another one. The first one was a true strong intervention effect. The second, 3, 4, 5. The first 5 predictions, they're all corresponding to true strong intervention effects. The 6th is not, the 7th is, the 8th is not, the 9th is, and then it levels off. The orange line here is a version which addresses the issue with the hidden confounder. So the good part here is really the first 5 predictions are all true strong intervention effects, but then we don't find much more anymore. Well, I try to recall, it's just a very challenging problem. You try to predict what happens here. And the first 5 times, if you prioritize, we have success, and then it's not so clear anymore. So I want to move a bit beyond this causality thing, because it is very ambitious, as we see in this example. And I want to come back to this worst case optimization risk problem and corresponding invariance. Mainly because this exact invariance and corresponding causality may be often too ambitious on a practical problem. Of course, this is well known. Scientists struggle since a long time with that question. And the other thing, which is maybe a bit slightly more mathematical, if you think in terms of perturbation strength, this causal solution is if you perturb arbitrarily strongly, but that might not be the case. So more pragmatically, we just want to construct a best prediction in a heterogeneous setting, and that leads to a novel robustness viewpoint. Okay, so we address this problem with what we call anchor regression and a regularization technique. And a slightly switched notation here. The environments, the perturbations which we've seen before, I have denoted them with EE for an environment, and now I call them the outcome of a variable A, and this variable A is called an anchor, and you'll see in a moment why I call it an anchor. But the model is somehow, here are my environments, my perturbations, they perturb the x's, they do not act directly on y, and here's the corresponding linear structural equation model. So people who are more knowledgeable about this, they say, well, this is the more realistic model, and this is a well-known model. This is the instrumental variables model, which is very, very popular in econometrics. So now there is this additional hidden confounder, right? And I want to say something, what are the causal relations between x and y? So the economists say A is an instrument, and they have exactly this structure that the instrument, in our case the perturbations, they act on x, but it's forbidden that they act on h and on y. In particular, that they do not act on H is a bit a hard or strong assumption because I don't know what H is. I have not observed in the data. So we relax this. So this is our model in graphical terms. I have this anchor. It can have an influence on hidden confounders. It can have an influence on Y. It's allowed now. It can have influences on X. I allow feedback loops. Now for this part of the talk, I look at linear systems. And the only assumption which we make is that A is a source node in the graph. That's why we call it an anchor. People in economics would say A is an exogenous variable, and so there comes this additional exogenous term here, M times A. Okay? That's my only assumption, A is a source node in the graph. Well, the environments, this anchor is now acting potentially on Y and H, and there's now a problem with that. There's a fundamental identifiability problem. You cannot find the causal solution anymore. You cannot infer the causal structure. It's impossible. But we regularize. We have something which we call causal regularization, and that offers something. It doesn't offer the causal solution, but it offers something which I think is quite worthwhile. One can actually show that one can still achieve a certain invariance. It's not an arbitrary invariance, but it's a so-called shift invariance. I'll define it later. And one can show that the residuals are shift invariant if and only if they are uncorrelated with my anchor variable A. So if you see this fact, then of course it's kind of natural to come up with an estimator like that. You have a regression problem, you minimize residual sum of squares, but you regularize your solution such that it is fairly orthogonal to A. Okay? It's not quite what we do, but it's a bit different technicalities. So this is our estimator. We formalize it with a projection estimator. We project on the column space of A. We look at the anti-projection of the residual length squared plus the regularization, and then the projection on A of the residual length squared. Okay? If gamma is 1, this is ordinary least squares. This is Pythagoras, right? If gamma is something else, we call this general causal regularization. You can put additional sparsity penalties on this. If it's a high-dimensional problem, you can do an L1 norm penalty. You can do some sort of other sparsity penalty if X is high-dimensional. So this is a convex problem. Well, I told you before, there's a fundamental identifiability problem. I cannot infer the causal parameter, but this causal regularization here, this one, this solves actually a worst-case risk optimization problem over a certain class F. And what is the class? The class F are shift perturbations. So what are they? So here is the definition. So I look first at the data generating model. This is kind of my linear structural equation. I have this anchor variable. This is exogenous term. This creates my heterogeneity. And now the perturbation model is shifts of that. I replace this exogenous effect by an arbitrary shift vector. So V is a vector, deterministic or fixed. It can act on all the components and it comes in dynamically into the system, so it's written this way. So V is a vector. It has a certain length, an L2 length, and the L2 length is measured by gamma. Gamma is just the length of this shift vector. There are other technicalities here which I skip, but I look at perturbations which are shifts and they have a certain strength, and the strength is gamma. Okay, so here is kind of quite a fundamental duality. We look at the population version of this problem. If you would have infinitely many samples, so then the projection is just a conditional expectation. And the theorem says for any regression parameter, you look at the worst case risk over shift perturbations. Okay? Shift perturbations of strength gamma. And that is exactly equal to somehow the population version of my objective function of my estimator. So it is here anti-projection on A length squared plus gamma. This is the same gamma here. So this is kind of the strength of your perturbations. This comes as the regularizer or the regularization term times the projection of the residual length squared. Okay? So worst case shift interventions correspond exactly to regularization, and now we have something, a much more handy vehicle. So regularized estimation, regularized computation is something very, very common, and we can employ it here to optimize worst case risk. So this holds for any B. We can think of this would be like my worst case test error. If I think of a prediction, well, I want to predict something which is in the future. It might be shifted. There's a worst case. And the worst case test error is kind of the criterion on the training population sample. This holds for any B, and of course then I can take the argument. I can optimize that. And if you do this, this leads to this estimator, right, the sample version. And this is in a way the explanation why this beta hat actually is good for protecting against worst case shift interventions. Okay? So this can all be made rigorous. The word therefore here is on this slide. I'm skipping the slide, but the idea is really on the population version we have this duality, and then it's kind of a more technical thing to derive this on the sample version. Okay. So let me show you a bit, at least, how this performs. Now we're in the prediction mode. So how does that work in practice? Here's a very simple example. So this is bike rentals in Washington, D.C. Okay? So they rent out bikes like in Rio, and you want to predict that what happens in the next 4 hours, what happens in the next day. The sample size is 17,000 plus. There are only 4 variables, 4 meteorological variables. And we just use a linear model. What is my anchor? My anchor, my environments, my perturbations is time. Maybe over time, the system changes, right? And so we take blocks of consecutive time points, and the unit size of a block is a day. And now if you do that, you gain over least squares about 15 to 25% if you evaluate worst case risk in some sort of a cross-validation framework. Okay? That's pretty good. So you can just simply improve upon least squares. And these ideas can also be used with other methods. So here we tried something with a nonlinear random forest algorithm. We could take any machine learning algorithm, which is kind of true. This is a problem on predicting air pollution in China. So we have different cities in China. The anchor is the geographical position of these cities. You run random forest, and again, you improve substantially over plain vanilla random forest, because the data is heterogeneous. Because the data is heterogeneous, it will probably be also heterogeneous in the future, and so this regularization actually helps. I'm not claiming this is the best thing ever to do your prediction, but the point is this is really a new way of thinking about scenario robustness. You want to be robust against new unseen scenarios. Let me conclude. There are, in my view, quite surprising connections between causality. This has been quite disconnected with invariance and stability and robustness. Some of it was known or were known. Havelmo, 1943, he knew that causality leads to invariance, but it has not been exploited the other way around. Some of them are novel, and I think especially interesting in the advent of large-scale data where you have heterogeneities, and the heterogeneities, the perturbations are very unspecific. You cannot describe it so well. In a way, it's statistics for perturbation data. I think this is an interesting newer area which will emerge. So I and many of us have been trained that somehow heterogeneity, non-stationarity is a bad thing, right? It's a nuisance. You want to get rid of it. I try to convince you it's a good thing. Make it your friend rather than your enemy. Thank you.
Yes, so we have time for perhaps these 2 quick questions.
So how about the use this for the predicted price? And then, for example, the stock price, because everyone loves the money. And then they use this method to the financial market and how to predict the price in the tomorrow or the future for the time series and also respective.
I didn't get the first part of your question, sorry.
Yeah, use this method to predict the price, stock, for example, stock price. in the financial market.
Wow.
And then this is time series analysis oriented. Yeah.
Potentially, of course, that's somehow in this regime of potential applications, although I think, well, I'm not an expert, but predicting financial prices, maybe you are an expert, is very, very hard. We actually are trying this on more economical predictions, kind of macroeconomics. So I have a student who tries it a bit on a macroeconomical problem. In principle, I agree, from an abstract viewpoint, this is potentially what we need. We need to be scenario robust. So potentially it could work in finance, but I think predicting in finance is very hard and I haven't tried it. Thank you.
So about the bike renting data, how did you do the estimate the error, the prediction error? Did you hold out a set that consisted of days or a random subset?
This one here? Yeah, that's a good question. That's actually a tricky one. How can you evaluate worst case risk, right? And because, so what we do, it is a holdout thing, but under some assumption, I must admit to that, you can translate this problem to a quantile problem, and then you have to look at high quantiles, how well you can estimate high quantiles, and that you can cross-validate. Otherwise, it's very hard. How the heck can you know, how can you do cross-validation for a worst-case problem? So it's a bit, we can have we can make an assumption, and then it's rigorous, but whether that assumption holds, that we have not validated on the real data set, right?
But in any case, the holdout was days, right? So was whole blocks that you hold out.
Excuse
right?
me?
You hold out a whole block, right?
Yeah. Here it's holding out a whole block. Here it's holding out cities. Yeah. Yeah.
So let's thank our speaker again.